All right, thank you so much. So thanks for the invitation and thank you to the organizers for setting up such an engaging and dynamic workshop. There's been a lot of good discussion so far, so I'm glad to be here. So I will be chatting a little bit about our approaches to extend this idea of flow-based Markov chain Monte Carlo, which you heard a little bit about from Daniello on Monday, to the context of SUN lattice gauge theory, which of course is highly relevant for applying this eventually to lattice QCD, which is an SU3 lattice gauge theory. So the contents of this talk are based generally on this set of papers. So a couple papers on flow-based MCMC in general, as well as a few papers that I'll dive into a little bit, extending this to the context of lattice gauge theory, and in particular thinking about how gauge symmetry plays a role in developing flow-based models. So let me just start off by reiterating, I guess, the motivations that we've heard so far for applying new sampling approaches to lattice QCD. So we heard on Monday from Kate a little bit about some of the existing problems, computationally speaking, that really obstruct MCMC sampling among other computational problems in lattice QCD. And in particular, we worry about critical slowing down and topological freezing, both of which set in as the continuum limit is approached. And of course, that's a very important limit to be worrying about. So this is an important direction to be able to make any sort of computational progress that we can, whether that be algorithmic or improvements in practical implementations or porting implementations to new hardware like GPUs. But my particular focus for this talk will be on the algorithm side of things. So how can we develop new techniques? In particular, how can we extend flow-based MCMC, which has been developed over the past few years, to lattice QCD-like problems? So the issues these issues, critical slowing down and topological freezing, really can be attributed to the local or diffusive nature of traditionally used Markov chain updates, things like local metropolis updates or HMC applied to lattice QCD. And the motivations then to think a little bit about novel sampling methods like generative ML models is that they can propose or directly sample configurations that could be used to propose global updates instead of local updates. And if you're efficiently proposing global updates, this could, at the very least, mitigate these problems of critical slowing down and topological freezing. So the way in which these sorts of models do so really is by providing what I like to think about as a flexible variational ansatz of a distribution, which we can call Q coming from the model. And the idea is, well, we can rewrite this, we're free to relabel this as e to the minus some effective action that the model is providing. And the goal is to variationally optimize this effective action or variational action to approximate the target action. So the target distribution that one aims to sample from in Euclidean lattice field theory typically takes the form of e to the minus action. Here, I've just pushed the normalizing constant up here. And the aim then is to make this effective action approximate the target action appropriately normalized. And I apologize, I have a sign error here. And the point of this, of course, is that the machine learned model action can be efficiently sampled sort of by construction. We're assuming that one has set up a model that one can push through to get samples from. So this idea of generative modeling has many applications in lattice quantum field theory. We've heard of many of them in the workshop so far. So for example, Lena mentioned on Tuesday that these flow-based models can be applied to precisely estimate the partition function, which can then give you handles on thermodynamic observables like the free energy in an asymptotically exact way as we take the number of samples large. And so we saw some nice plots along the lines of these where the flow-based estimates of free energies are far more precise than HMC approaches to the same. But they can also be applied in improving or replacing HMC updates. So one can think about applications of flows or invertible neural networks really to describe modified transformations in the space of configuration paired with conjugate momentum. So HMC evolves this via some symplectic, approximately energy conserving way. But Sam will, I think, follow up on this talk immediately afterwards and tell us a little bit about how these machine learning approaches can be applied instead and potentially avoid problems like topological freezing, as mentioned previously, where the same sort of guarantees as HMC, namely detailed balance, still apply. And the way in which this is sort of achieved is by plugging in the learned parts of the transformation in very particular places in the updates to the pair of field configuration and conjugate momentum variables. Now, the focus of this talk, and this is sort of a follow-up to Daniela's talk on Monday as well, is to apply these flow-based models sort of to directly propose new configurations where you can then apply a metropolis step for exactness to either accept or reject that proposal and end up with a global looking update. But to tie these approaches all together, I think the reason why we're seeing some success with all of these sorts of approaches recently is we're sort of building up ways in which these black box machine learning components can be wrapped inside exact schemes. So we see that, for example, in this HMC update, the black box neural networks live in very particular places. Similarly for flows, there's very particular ways in which the neural networks appear inside a much more precise and specified architecture where you have some guarantees that eventually give you exactness. And that seems to be a key step in any applications we're thinking about to things like Lattice QCD, where you really need that systematic control to make useful calculations that inform us about experiments and about the standard model. So let me then, in that lens, just briefly review the construction of flow-based models and flow-based sampling to set up this talk a little bit. So the idea, this is sort of a bottom-up description, is we can think about starting with convolutional neural networks as black box local function approximators. So this is schematically a picture of convolutions. You apply the same linear kernel to transform your input field to the next layer and then the next layer and so on. So this kernel would scan over the whole thing with the same set of weights. So it's both local and translationally equivariant. And that can be put inside what's known as a coupling layer. This is one example of an approach to build a flow-based model in which you split the degrees of freedom of your field. Some set will be frozen and are used as inputs to this neural net, and the other set will be updated by a very precise, so this could be a very specific update function that takes outputs from the neural net and applies them to invertibly transform these elements. Could be something like a scaling or an offset based on these parameters. And that manifestly allows invertibility. We can run this backwards, and we can also compute the Jacobian of this transformation. And by doing so, we then have a component that allows us to squish and stretch probability density, sorry, in a very known and understandable way, and yet a very trainable way. So it allows us to tweak the neural net component independently of anything else, and independently, in particular, if the invertibility guarantees and the fact that we can compute the Jacobian. And then we can combine these coupling layers into flow-based models where composition of multiple coupling layers allows very dynamic and expressive definitions of transformations of the field configurations. And if we start from a known prior density, this squishing and stretching gives us some new density that's computable. Now, importantly, we can also train this. So as was mentioned on Monday and in a number of other talks, we can measure the KL divergence, for example, between this output distribution and the target distribution, and then apply gradient-based optimization to update the parameters of all of these black box neural networks. And we can get guarantees of exactness because we have this calculation of the density, and we have the calculation, of course, of the target density up to normalization given the action. And so one can apply things like Roux weighting, or in the works that we apply, or that I'll discuss in this talk, we can apply Markov chain Monte Carlo using a metropolis accept reject based on these weights. So the main focus of this talk is in particular thinking about how we can take this approach, this method based on flow-based models and their exact sampling, and extend it naturally to the context of lattice gauge theories. And so an important component, of course, of lattice gauge theories is that it is a very large symmetry group, namely the gauge symmetries. And we would like to encode this in our models. And one way to do so, this is just one particular approach, but it's the one that's used in the set of papers that I mentioned, is to think about making that prior distribution I just mentioned invariant to these transformations. So updating the input field does not affect the density. And making the flows that are transforming your configuration after sampling from the prior equivariance to these transformations. So the transformation commutes from application to the input to application to the output. And the result of this is then a symmetric model that one can use to approximate the target distribution, which of course also satisfies the symmetry. And the motivation for doing this is one can hope to reduce the data complexity of training as well as the model parameter count, because schematically, if you think about this, for example, in this picture on the right, the symmetry directions, which in the schematic diagram are the rotational coordinates, do not need to be parameterized, and they also don't need to be trained. You could think about, if I'm just optimizing a model that's guaranteed to be absolutely rotationally symmetric, the only parameterization and training that I have to do is on the radial coordinate alone. Whereas if I were to give a very generic model and try to learn the symmetry, or learn the distribution that has the symmetry, of course, I could do so, and you might get a nice approximation to that distribution, but you're doing so in this larger space with more parameters and potentially more training complexity. And so this idea of baking symmetries in is not exclusive to flow-based MCMC. There was a talk by Di Luo on Wednesday, and Akira Tomiya will also talk about approaches to baking in gauge symmetries to neural nets on tomorrow. But our particular interest, of course, is working our way towards flow-based MCMC in this talk that incorporates SUN gauge symmetries, which of course are very relevant for lattice QCD, also plus or minus a small detour into U1 gauge symmetry for a bit of an introduction to how the general gauge equivariant architectures work out. And to do so, I'll focus on pure gauge theories, but I'll point you to Danielo's talk on Monday, as well as an upcoming paper with these set of folks on incorporating fermions into flow-based models. But it's a bit orthogonal to the question of how we incorporate SUN gauge symmetry at this point. So these studies will revolve around theories that are pure gauge and that use the Wilson gauge action, although that's not any particular constraint of the model. It's just a useful prototypical gauge invariant lattice action that I imagine everyone here is familiar with, that's written in terms of plaquettes that look like these product of 4 links around a loop, and describes then a lattice Euclidean path integral that's given in terms of these link variables that are the fundamental gauge degrees of freedom. And the key point that we're trying to achieve is ultimately to produce a model distribution that's invariant under the gauge transformations that look like this form, conjugation by matrices on either side, where the matrices are arbitrary parameters describing this large gauge symmetry group. So first thought would be, well, why don't we apply gauge fixing? I mean, just get rid of the pure gauge degrees of freedom, then you're good to go. You're only acting, I mean, in that schematic picture, this would be like getting rid of the rotational coordinates or the angular coordinate. You're only then acting in the direction that you care about with your flow and then in terms of your output distribution. But there are some issues with that, and we've actually had some discussion already in this workshop about these issues, I think. So to highlight these points, first we can imagine, well, what if we did an explicit gauge fixing where these degrees of freedom are completely sort of actually explicitly factorized out, and we could set the pure gauge degrees of freedom to 1. So an example of that would be a maximal tree gauge fixing where, for example, these bolded links could all be fixed to 1 simultaneously. But an issue with that is that it's at odds with translational symmetry and locality. So just to highlight that issue, we can look, for example, in this maximal tree. This is just one particular maximal tree gauge fixing scheme. It looks a lot like temporal gauge. And the issue is sort of highlighted by the fact that this link, for example, in the gauge fixed configuration, which is one of the remaining dynamical degrees of freedom, in the non-gauge fixed corresponding configuration, it really encodes information about this Wilson loop surrounding the shaded region. And similarly, a link higher up would be encoding information about a larger Wilson loop. So these links all encode information about very different looking physical degrees of freedom. So there's no sense of translational invariance here. At least translational invariance is broken in one of the directions in this case, because the statistical properties of a link encoding a 1/3 Wilson loop are going to look very different from the properties of a 1/4 and so on. And this is also violating locality, because these degrees of freedom are encoding, if I think about a link very high up, far up at the top of this lattice, it's going to be encoding information about a long string of plaquettes forming a Wilson loop, or a long, I guess, chain of links closing a Wilson loop. So these are not insurmountable problems. One could imagine discarding locality and translational symmetry, constructing a flow-based model for these degrees of freedom anyway. But as previously mentioned, we would like to encode as many symmetries as possible. And furthermore, locality gives us nice ways to construct sensible flow-based models with few parameters based on these convolutional neural nets. So these are all important things that we'd like to preserve, and we in fact can do so based on the work that I'll just chat about in just a second. But a second thought is maybe we could instead use implicit gauge fixing scheme, something like Landau gauge, where we fix by minimizing some function of the gauge transformation of a gauge field. And in doing so, this is a manifestly translationally invariant function and local function. And so minimizing it should give us some sort of translationally invariant scheme for gauge fixing. But the problem with this is just that it's unclear how one can invertibly transform in this subspace, which is implicitly defined rather than explicitly defined. So in maximal tree gauge fixing, we just removed the pure gauge degrees of freedom by fixing them to 1. In this gauge, yes, we've removed pure gauge degrees of freedom, but it's unclear, how do I write down the reduced set of SUN variables corresponding to only the gauge invariant components that I want to transform. So our approach then is to think about, well, let's forget about gauge fixing. It seems to have difficulties, and instead just act on the unfixed link representation itself. And to achieve then gauge symmetry, we can work with architectural approaches to carefully architect our flow-based model such that this invariance to the symmetry is preserved exactly. So to do so, I mentioned that one requires invariance of the prior and equivariance of the flow, or it's sufficient rather to make an invariant prior and an equivariant flow. And an invariant prior is actually very straightforward to construct. So one can just set up a uniform distribution, for example. This is just written in terms of a probability density equal to 1. Any gauge transformations of this obviously leave 1 equal to 1. And so this is very straightforward. One can sample it directly by sampling with respect to the Haar measure, and then the prior distribution is handled. But gauge equivariance is a little bit non-obvious. We would like these, these link transformations where you act by matrices on either side to commute through applications of each coupling layer, so that therefore it commutes through the application of the whole flow. And the way in which we do so is to think about, instead of acting on links directly, to do a bit of a temporary change of variables and act on untraced Wilson loops. And the reason for this is that these loop transformations of untraced Wilson loops, which we can draw with an opening somewhere, will transform according to matrix conjugation. This is just standard gauge transformation properties if I combine this product of links. But it transforms by the same matrix on either side. And that actually turns out to be a big advantage in terms of enforcing equivariance to the symmetry. And of course, if I'm working with loops, we should keep in mind that a closed loop would be gauge invariant. And so closed loops form useful gauge invariant quantities that one can use as inputs as well to neural networks without spoiling gauge transformation properties. So let's dig in a little bit to the details of building this coupling layer. The idea is that one starts by computing a field of Wilson loops. So for every originating site, we compute the Wilson loop of a fixed shape, translated across all sites. We can do this efficiently in parallel, simultaneously. And we split the coupling layer into some inner coupling layer and outer coupling layer. So the idea being that the inner coupling layer proposes some sort of active transformations on a subset of these loops. So proposes that I update some set of these W's to some W prime. And it may condition on some set of frozen loops, which are gauge invariant, so those don't affect our gauge transformation properties. But of course, finally, we're interested in working in the link representation. So we wrap such an inner coupling layer in an outer coupling layer that handles that proposed transformation and essentially says, what do I need to do to the links to make that transformation happen? And the way in which this is done is by just taking any proposed transformation of a loop and splitting off the first link and saying, I'll just update it in the following way. I'll update it so that I get the right desired W prime by transforming just this link and freezing everything else. That's just one way to make such a transformation property work out, but it turns out to be sufficient to learn effectively distributions in the applications I'll talk about in just a second. So an important point, though, there's a few subtleties here. There's, for one, the fact that if I update this link, maybe that link was included in some other subset of links that would pass the intercoupling layer. So those set of links transform in a way that we label passive transformations. So it wasn't something proposed to be transformed by the intercoupling layer, but it was accidentally or passively transformed. And a key point is just that we have to exclude such passively transforming loops from either the actively proposed subset, which would, if we propose a transformation, but it accidentally transformed in a different way, that would be conflicting. It wouldn't give a consistent link picture of what we want to happen to the loops. And we also have to exclude them from any frozen closed loops that we pass as inputs to the neural nets defining these transformations, because that would break invertibility. What we would want to be frozen inputs to black box neural networks would have transformed as a result of the action of the outer coupling layer. But finally, sort of the key feature that makes this gauge invariant is the fact that the intercoupling layer active transformation has to satisfy this matrix conjugation equivariance. So if I do a gauge transformation to my loop, which amounts to conjugating my matrices on either side, then that should be equivalent to just gauge transforming the output of what we call this kernel acting, defining the transformation that the intercoupling layer proposes. So just to give a concrete sense of what these active, passive, and frozen loops could look like, let's say, for example, that the outer coupling layer was defined to attempt to transform only the links that are bolded in black. Then these gray loops would be perfectly fine to provide as frozen inputs, because of course they cannot transform. We're never going to transform any of these dotted links. That's the guarantee that the outer coupling layer provides. And the intercoupling layer has to then propose transformations of loops that start with one of these bolded links and that contain only frozen links outside of that, so that we can compute this transformation of the bolded link at the end of the day. So examples of these include these sort of red bolded loops where the first link is a link to be transformed and the rest are all frozen, such that after we propose some transformation of this, we're eventually able to implement it at the link level by transforming just that one bold link. Now, a concrete implementation of this, one that we actually use for the applications, is this PAFF, passive active frozen pattern, in which the loops are always plaquettes. The active transformations will be one of these loops, just in this case to the right of the links to be transformed. We ignore these passively transforming plaquettes to the left because they would spoil our properties of interest. And we pass these stripes of frozen plaquettes as inputs to as gauge invariant inputs to our functions defining the transformation properties. Okay, so that's all rather technical details about how the gauge equivariance actually works, but kind of at the intuitive high level, the idea is that loops are sort of a nice object to choose to transform, both because they have nice transformation properties, but also because they encode sort of physically the information, the gauge invariant information that one would be interested in. If you think about taking traces of these loops, that exactly gives you these Wilson loop quantities back that encode gauge invariant quantities, and in fact can be shown to provide a basis for all gauge invariant quantities that one is interested in. Okay, so with that in mind, let me just chat about a few applications that we've looked into of these sorts of gauge equivariant coupling layers. So the first was to U1 gauge theory, and for that we require U1 kernels that satisfy this matrix conjugation equivariance. But as it turns out, conjugation equivariance for U1 is trivial because the transforming quote unquote matrices, or really they're scalars for U1, will just commute through and cancel. So what we're really interested in is just invertible maps on U1 variables. And that really is only a few steps away from invertible maps on non-compact variables, which have been explored thoroughly in the flow-based literature, but did require some extension. So for details, you can check out this paper. But the idea being that via a few tricks, one can address the periodic and compact domain. For example, you can just project into a non-compact space, transform there and project back, or you can work with splines that very directly understand the minus pi to pi interval and invertibly transform it. I won't go into any details, but I'd be happy to answer questions later if anyone's interested. But these kernels can then be used to construct equivariant flow-based models, and were applied in the study to two-dimensional U1 gauge theory, again using that Wilson gauge action. The reason for working with 2D is, one, you can get analytic results there, 2, the computational cost is cheaper, but 3, there's also an exact lattice topology in 2D. So there's a topological charge one can define, and it turns out to mix very slowly. If we look at the HMC Markov chain history of topological charge and the heat bath and other sampling scheme trajectory, these mix very slowly. Whereas in comparison, when we train and sample via flow, one gets very rapid sampling from this topological distribution, and one can precisely estimate things like topological susceptibility. And for example, if we then go to measure things like the autocorrelation time of that topological charge, the flow-based model provides a far more rapidly mixing version, of course, of estimates of that topological charge. So of interest, and I guess sort of the main interest of this talk is how do we then extend that to SUN variables? And in this case, conjugation equivariance is non-trivial. There actually is some constraint that one must apply to your kernel function to satisfy this equivariance to conjugation by some gauge transforming parameters. But there are a couple of useful observations we can make that motivate our strategy here. So one is that conjugation really only rotates the eigenvectors of that matrix that we pass in, whereas the spectrum remains invariant. And the Wilson loop spectrum is also the thing that's encoding gauge invariant physics. If I take the trace of this, which is just a function of the spectrum, you get Wilson loops, and the set of all Wilson loops form the basis of gauge invariant observables, where I'm including things like non-contractible loops in that set. And so this really is the thing that we also just want to transform, is just the spectrum itself. So the strategy overall here was to invertibly transform only the spectrum via what's known as a spectral map, or what we introduced in this paper as a spectral map or spectral flow. So I'm a bit short on time, so actually I'm going to skip the details of how we do this, although I'd be happy to come back. But the general idea, I'll just highlight one point, is one can take the matrix W, diagonalize it, so extract out those eigenvalues, and then the key feature that one requires is permutation equivariance, because these eigenvalues come out in some arbitrary order, and you don't want to be sensitive to your diagonalization procedure. So there's an interesting relation here actually to things Jesse was talking about on Wednesday about permutation invariant neural nets, but here we were not able to apply a generic permutation invariant net. We actually had to construct sort of from the ground up specialized tools to satisfy the determinant constraint at SUN and the fact that these are unit norm complex numbers. But I'll just skip all of that and just point to the fact that we then were able to construct kernels that very expressively were able to capture distributions on single SUN variables that satisfied this conjugation equivariance that, for example, resulted in very good agreement on a variety of different distributions here labeled C1, C2, and C3, and on a variety of different gauge groups. So this goes all the way up to SU9, for example. One can see the very complicated structure of the Haar measure combined with this probability density in the space, but the flow perfectly captures it, and in fact is perfectly equivariant under the symmetry of interest. And same thing for SU3 and SU2. So finally, we applied this to SU2 and SU3 gauge theory to test really, are these kernels, is this PAFF masking pattern, are these all sufficiently expressive to make progress? And in the study, we worked with 16 by 16 lattices in particular, just to work with a non-trivial number of degrees of freedom, but in a computationally tractable application, and one in which we also, again, had analytic results to compare against to confirm that the model was doing sensible things. So for a range of different values of beta, we trained these flow-based models based on 48 of these PAFF coupling layers each, which effectively update all the links in the lattice 6 times in total, so that it's a reasonably expressive, model, but not one that's exorbitantly expensive to evaluate. And this set of theories, SU2 and SU3 gauge theory, unlike U1, had no equivalence to topological freezing. So the study that we did was essentially to focus on the absolute model quality instead and ask, do we get good approximations to the target distribution rather than looking at a slowly mixing quantity like topological charge? And of course, because we're using these PAFF coupling layers, all model distributions exactly satisfy gauge symmetry. So the one slide summary then of the results here is that the trained flow-based models, once we apply this Metropolis Hastings step to get an MCMC procedure, give observables that agree with the analytic results. And of course, they have to, because this MCMC is asymptotically exact, but even for the finite sample sizes we were working with, we didn't observe significant artifacts. And in fact, we went and measured things like the autocorrelation time and found that generally in these MCMC chains, the autocorrelation time of all observables is relatively short. But then jumping back to that sense of absolute metrics that we were looking at, we compared and evaluated, I guess, the effective sample size of samples drawn from the model and the result of their statistical power on the target distribution. So an effective sample size really is giving a measure of, if I were to reweight from samples drawn from the model, how many effective samples would I get of the target distribution, or what percentage would I get as effective samples? And one can see that these are all above approximately 50%. So you're doing no worse than 2 times as inefficient in this case as just directly sampling from the distribution of interest. So we also studied the transformation properties under symmetries that were only partially or not at all enforced in the model to understand whether the model had learned anything about these symmetries. So for example, for the translational symmetries, a key point of this work is to enforce gauge symmetry while preserving translational symmetry. There is some breaking of translational symmetry down to a subgroup based on these masking patterns that themselves are not translationally symmetric exactly, but are translationally symmetric under translations mod 4 in this case. And so one can see that under translations here, this index is just enumerating all possible lattice translations on a 16 by 16 lattice. And these traces are of a particular base configuration transformed in all ways, and measurements of the effective model action versus the target action. One can see, first of all, that these lines more or less correspond on both sides. So the effective action is learning to approximate the target action pretty well. But also within each of these transformations of a configuration, there's very little fluctuation, relatively speaking, to the distribution over possible magnitudes of action that one could draw, whether they be less likely higher action configurations or more likely lower action configurations. So the translational invariance, the residual translational invariance essentially was learned. And rotation and reflection symmetry was not enforced at all, but was also essentially learned, as one can see by the correspondence and the near invariance under all 8 2D rotation and reflection symmetries. So let me just summarize then by saying that via these gauge equivariant coupling layers, this provides a way of encoding gauge symmetry while preserving most of translational symmetry, as well as locality in these models. So we get kind of the best of all worlds in some sense, but it requires the implementation of these particular kernels that satisfy some matrix equivariance properties. And we provided some implementations in those papers that I mentioned, but it's not necessarily the only implementation that one can use. As long as these properties are satisfied, a gauge equivariance and therefore a gauge equivariant flow and therefore gauge invariant flow-based model results. And these could be applied then to produce high quality models for these sets of lattice gauge theories that served as proofs of principle that these gauge equivariant coupling layers really do work. So there's a few future directions that come to mind that are kind of natural things to develop upon this work and in some cases works in progress already. So for one, obviously we'd like to go to 3+1 dimensions. And to do so, there's no theoretical obstacles, but maybe practically speaking, one might want to change that masking pattern, what sorts of loops you use, and so on. Also, when we think about things like center symmetry breaking or other symmetry breaking in different lattice field theories, one is interested in training from multimodal distributions. And it's not clear what the right training procedures are based on past work, but see this upcoming paper for some more details on how one might be able to effectively train when a multimodal distribution is involved. I also didn't mention at all any of the optimizations. Sorry, I didn't mention any optimization of the training hyperparameters, things like what optimizer, learning rate, and so on that we used, or the model architecture. And the reason I didn't mention it is that we did very little of that for this proof of principle study. The idea being that if you can just throw a very generic model at this problem and get good results already, then we can defer thinking about these sorts of questions for when we need to work at scale. But it is still an important question for scaling up. And finally, of course, we'd like to include dynamical fermions. So I'll point you to this upcoming paper as well for that. So let me just conclude then by pointing to a few open questions that maybe prompt some questions now or discussion later. So one thing that comes to mind is, in what limits are these sorts of flow-based models universal? The nice thing about black box neural nets is we know that as we take the width of the hidden layers large, you get an arbitrary function approximator. But it's unclear whether there might be some sort of silent expressivity failures in these sorts of models. We don't see those because we're effectively training models that capture the distribution right now, but maybe as we scale, we run into those, and one would be interested in either avoiding or more generally diagnosing these expressivity failures so that you know that you need to extend the expressivity rather than running into training problems potentially as an alternative reason for low quality models. Second point being, maybe we're interested in working with hierarchical structures. I mean, we know a lot from the physics side based on things like asymptotic freedom, the renormalization group. So flows architected to take advantage of that could perform much better. But it's unclear exactly how one should provide that architecture. And finally, of course, the all-important question is, how should the model be scaled? In what way should one increase the expressivity of the model and modify the training of the model as the continuum limit is taken? And how does that scale the computational cost of these models? And I'll point to this paper that actually was posted last night on the archive with some thoughts. I unfortunately haven't had time to read it in detail, but it seems like this paper provides some interesting directions for how one should investigate that question. So I'll conclude there. Thank you very much for your patience, and I'll be happy to take any questions that you have.
Thank you very much, Gurtej. A very nice talk, very impressive work. So we're open for questions. Just change my view. Yeah, I see a question by Lena.
Yeah, hello. Thank you very much for this very interesting talk. I have two questions. So the first one is about this autocorrelation time. So you reintroduce a little small amount of autocorrelation due to that metropolis step, right? So because you still have a Markov chain. And so I was wondering why exactly you really need it, because in our case, we don't have any autocorrelation time left, because we argued that due to that imperfect training, of course, we have a bias, but it's subdominant with respect to the variance of the estimator. So then it's kind of negligible, but is there an additional reason why you are using that additional metropolis step, or could you also get rid of autocorrelation time completely?
Yeah, that's a great question. So certainly one could choose other ways of enforcing exactness. It doesn't have to be via this Markov chain with, as you say, the rejections introducing residual autocorrelations. So one thought is, one could apply reweighting, which really amounts to just providing a different estimator for observables of interest under the model distribution rather than under the target distribution with guarantees of exactness. But the sort of trade-offs here, I guess, are that what results in autocorrelations in the Markov chain side are rejections amounting from cases where your model distribution doesn't accurately model your target distribution. And the corresponding computational challenge then in a reweighting approach is that these ratios, the reweighting factors of the target probability density over the model might have high variance. And so the effective sample size that I mentioned is a way of measuring in the reweighting picture what you lose, what statistical power you lose due to this variance, and sort of serves as the analog of autocorrelations in the Markov chain side. And so really we expect that a high quality model will give a good reweighting estimate as well as a good flow-based MCMC estimate, and a low quality model will give a poor reweighting estimate and a poor flow-based MCMC estimate. But there might be different use cases. So one point on this slide is that if the observables are expensive to compute, then you're wasting your time computing them on downweighted samples if you use a reweighting approach. Whereas in flow-based MCMC, you just discard and reject those samples and never have to compute on them. So there's some trade-offs here. And conversely, if the observables are cheap to compute, then maybe you prefer reweighting for the simplicity and for not having to worry about things like burn-in time and so on. So you just have that asymptotic guarantee in terms of proposed ensemble size.
Okay. Yeah, thanks for the answer. Another question was about the convolutional neural networks that you mentioned. So of course they would preserve translational invariance, which is beneficial, but at the same time, isn't it harder for them to approach phase transitions? Because then when we have long range interactions, we would need a very deep neural network because we have local operations there. So if we want to model long range interactions, we need to stack a lot of layers behind each other.
Yeah, this locality is certainly, I would say, a trade-off. So it makes your coupling layers as a whole local, and so they're really only mixing information within a few sites when we apply these convolutions and then apply these local transformations. So maybe one would be interested in replacing convolutions with things that are translationally invariant, but also have the ability to account for global information. So there are ways that one can imagine doing this. For example, if I include pooling operations that take my whole lattice down to a scalar and then use those to condition upon, that brings global information back in without sacrificing translational invariance. And there may be compromises here where one can imagine hierarchical convolutional structures, things that do some partial pooling, something along those lines, and then scale back up, because eventually you need a full lattice worth of parameters for these coupling layers, which would then maybe partially violate the exact translational symmetry in your model a bit further, but then maybe gives you more global information and more efficient updates. So ultimately, I think you're right that one has to think about this locality, especially as one approaches criticality, things like the continuum limit. And this goes back to, I guess, this open question of what are the right model architectures to think about continuum scaling? Should one just stack up more coupling layers as you go towards the continuum? Will that give you a more efficient computational scaling versus traditional MCMC, or are there better ways to implement these neural nets and architectures? I think that's very much an open question.
Okay, thank you.
Okay, I see a question by Bastian.
Yeah, hi, thanks for the very nice talk. So I have maybe a very naive question since I'm new to all of this. So you're basically using this as a metropolis, right? So in order for the metropolis accept reject to only work with the actions, you need a symmetric proposal probability. So how is that ensured with proposing that with this neural network? I might have missed this, or?
Yeah, sorry. I unfortunately don't have a backup slide on this, but the metropolis accept reject step here is not a function only if the action, because as you said, it's not a symmetric proposal. So in fact, the metropolis accept reject probability takes the form of ratios of the target distribution to the model distribution for both the old configuration and the proposed new configuration.
Okay, I see. Yeah. All right, then I understand. Thanks.
All right. Yeah, so thanks for having me. My name is Sam Foreman. Today, I'm going to be talking about some of my recent work on using deep learning to improve basically build better Markov chain Monte Carlo sampling techniques. So I'm not going to spend too much time going into kind of the details behind this, since obviously a lot of this has been covered, and I think for the most part, people are somewhat familiar with this. Just to kind of give some acknowledgements and thanks to the people who have helped me. So this work, all of this work has been done in collaboration with Zhao Yang and James, both at Argonne, and and then also I would like to thank, obviously, so Norman and everybody in this critical slowing down group that I've been working with. The data science group here at Argonne has been useful in helping things get going and take advantage of the computers and resources available. Yeah, and so I just want to say thanks to everybody. I'm sure some of them are on here.